Hey everyone, and welcome back to the channel. Today, we're going to be talking about a powerful technique called memoization. This is a way to optimize your code and make it run much faster, especially when you're dealing with recursive functions. We'll be using JavaScript for this demonstration, but the concept applies to many other programming languages. Let's start by implementing the classic Fibonacci sequence calculation, the slow, traditional, recursive way. We'll call our function Fibonacci slow. The Fibonacci sequence starts with 0 and 1, and each subsequent number is the sum of the two preceding ones. So Fibonacci 0 is 0, Fibonacci 1 is 1, Fibonacci 2 is 1, Fibonacci 3 is 2, and so on. Now, every recursive function needs a base case to stop it from running forever. For Fibonacci, the base case is when n is 0 or 1. We just return n in these cases. If this base case is not present, the loop will run forever, causing a call stack overflow error. In the recursive case, which is when n is greater than 1, we make recursive calls to Fibonacci slow n-1 and Fibonacci slow n-2. Notice how, as n gets larger, we're repeating a lot of the same calculations. For example, calculating Fibonacci 5 involves calculating Fibonacci 4 and Fibonacci 3, but Fibonacci 4 itself requires calculating Fibonacci 3 and Fibonacci 2. See the redundancy? This makes the function very slow for larger numbers. That's where memoization comes in. We'll create a new function called Fibonacci fast. This time, it will take two arguments, n and memo. Memo will be an object with key value pairs as the number and its Fibonacci number. Each of the results of our calculations will be stored in it. Think of it as a cache. This is the key to avoiding repeated work. We initialize memo to an empty object. If a memo object is not passed in, it will be this empty object. This line, if n in memo, is crucial. It checks if we've already calculated the Fibonacci number for this n. If we have, we simply return the cached value from memo n. If not, this is the first time we encounter this n, so we proceed to calculate it recursively. Here's the same base case as before, and this recursive step is similar too, but notice, every time we call Fibonacci fast, we pass along the memo array. This way, each recursive call can access and update the cache. Now the crucial part, we store the result of the calculation in memo n. This is where the magic of memoization happens. The next time we need Fibonacci fast n, we'll already have it in our cache. Finally, we return the cached value. Before we proceed, let's understand how memo is accessible between recursive function calls. It is due to closures in JavaScript. Due to closure, all successive Fibonacci fast function calls have access to the same memo object created initially with all the updated calculations stored in it. For example, this is how the memo object will look when we have calculated Fibonacci fast 15. So when we calculate Fibonacci of 16 at this line of code, we will have memo of 16 equal to Fibonacci fast 15, memo plus Fibonacci fast 14, memo. But since we already have memo 15 and memo 14, the recursive call will simply return their values, and we will have Fibonacci of 16 almost instantly. Let's see how much of a difference memoization makes. We'll use date.now to record timestamps before and after each function call. We'll calculate the 40th Fibonacci number. That should take a while for the slow version. A little housekeeping. We'll add some console logs to make the output more readable. This is good practice, especially when debugging performance issues. Clear output helps you quickly see where the bottlenecks are. Alright, let's run this using Node.js and see the results. As you can see, the slow version takes over a second, while the fast version takes 15 milliseconds. That's almost 100 times faster. Wow, that's the power of memoization. It turns an exponential time algorithm into a linear one. This will make a significant difference when we calculate larger values. For context, I will add Fibonacci of 100 using each of these methods at the end of the video. Memoization can also help prevent certain types of bugs in recursive functions. For example, if your recursive function has side effects, memoization can ensure that those side effects only happen once for each input, avoiding unintended consequences. It can also help prevent stack overflow errors by dramatically reducing the number of recursive calls. Thanks for watching, and see you in the next one.